going to hand around some of our finished parts. Just so you guys can see them, it's a little easier to see up close. So just please pass these around to everybody. We'll start on this side. Try to make it so it gets all the way over to the other side. Thank you. All right. Thank you guys for coming. I appreciate you sticking around until the very end. Or not quite the very end, of course, but the last senior project. We are Prosumer Technologies, and we are making a small-scale 3-axis CNC milling machine. My name is Joe Rutledge.
My name is James Berger.
My name is Michael Eisenhart.
I'm Chase Osborne.
And I'm Matthew Schreiber.
So some of the topics that we're going to cover during this presentation include the inspiration behind this design and why we chose to go forward with this, the requirements that we need for a success, the design itself, which will include 2D and 3D CAD, the physical build, which was manned by James Berger, the design challenges that we faced throughout the entire process of the entire 2 semesters, the budget that we came to when it was all said and done, some of our testing and results, which include some of the things that are being passed around right now, future considerations and how we can potentially improve this in the future, and lastly, we'll finish with our thanks and acknowledgments for how we got this one. To start, our inspiration behind this project was actually the additive manufacturing boom that's been in the news in the past couple of years. Most people refer to it as 3D printing, but that's actually a larger genre that can be subdivided. Most people think of 3D printing as the FDM printing, which is where the metal extruder will extrude molten plastic. There's many more forms, of course, but that's the most common, and it is actually, just in the past few years, already gotten down to the small-scale home use. Some of the machines can be as cheap as $300. What's interesting is subtractive manufacturing, which would be like a lathe or a mill, so turning, things like that. They haven't quite reached the small-scale market in the same way. The cheapest product that we found that would be comparable to our capabilities that we've achieved would be somewhere around $4,000. So we've done a little bit better than that, and that was the overall goal, was to try to get this down to a level where it could be maybe consumer use or, more importantly, for educational use.
So just to touch on the requirements that we chose, actually beginning of last semester, this was our goals. We wanted to build a volume of 16 inches by 16 inches by 10 inches deep, which is, for anyone who knows millings, a pretty decent sized part for a mill this size. We wanted to maximize our tolerance at plus or minus a 16th of an inch, which isn't great. It isn't great for a production mill, but for an educational purpose, it would be sufficient to do the calculations that are required in the classroom. Excuse me. We want to keep our gross expense at $1,500. As Joe just said, there are subtractive manufacturing products on the market. They make much smaller parts and they're much more expensive. So we wanted to improve on that. Lastly, we wanted to be able to move this part around from classroom to classroom, in this case with our mill, and be able to plug into a 110 receptacle so it can be used anywhere in the building.
So above is a very basic block diagram of our design layout for our CNC machine. It starts with a computer which has our CAM and CAD software on it, and from there you essentially go to a breakout board, which is then connected to our VFD, stepper drivers, and e-stop button. The VFD is connected to our spindle, and it actually controls the spindle speed. And the spindle holders are cutting tools which will cut apart. And the stepper drivers, they are programmable using dip switches. You can change the microstep values, which can improve your tolerancing. And those are connected to your stepper movers.
So, as stated previously, the end goal of this project was to create a machine that would give students a first-hand look at the subtractive manufacturing process. This was done by creating a machine that can be easily transported into a classroom, but is still durable enough and robust enough to machine harder materials such as aluminum. In order to achieve this, we built the frame out of strong, lightweight T-sawn aluminum extrusion. This helped us to easily mount parts to the frame to construct the entire build, and it also allowed us to fine-tune these parts to give us a more accurate tolerance. Our build plate for the machine is a piece of 1/4-inch steel plate. This gave us a nice flat surface to mount our workpiece to help the machining process be more accurate. In order to control each axis is mounted to the frame by means of these carriages, which contain 3D printed rollers. This helps create a smooth linear motion to reduce binding and shatter in the itself. And then each one of these axes is controlled by a high torque stepper motor. And this stepper motor is coupled to a fine pitch lead screw, again, to help with our tolerancing. And then this brings us to the overall build of our machine. Obviously, the render is just the mill itself, but there's a lot more that goes into this, as Jay stated previously. Everything is on this cart, so it is very mobile. It can be pushed right into a classroom and plugged into the wall. We have our computer, which contains our CAM software, so you can just put a model of the part right in there, and then you can start machining it. On the second shelf here, we have our electrical box that contains all of our controllers and everything to control the mill. And on the bottom shelf, we also have a bucket that has a pump for the spindle itself. The spindle is water cooled, so it helps keep it running smoothly and efficiently.
Some of the design challenges we came up with, as Mike just mentioned, are roller carriages on each axis. In our Z we have two, in our X and our Y we have one. We had a problem with binding and chatter, so we had to, in the Z direction, stop the Z axis from wobbling as it went up, which would make it fine. So to do this, we ran initially a pulley system with a belt that would drive both lead screws up at the same time. The problem we ran into with that was the belt was slipping, and we couldn't get the proper tension without breaking the belt or creating too much pressure and actually drawing our lead screws in, which was destroying our tolerance. So we eventually moved to a chain and sprocket system with a 1-to-1 ratio. And then along the same lines, there were our major issues. There were some minor issues that came up, and there were major issues. We're binding also in the y-axis. To stop this, same concept, we have that wobble going back and forth as you have a 24-inch piece driven by one lead screw in the center. So you're going to want to move like this. So we use two linear rails, also made out of 80/20, to guide that axis in a straight direction. Now moving into our budget, as you can see, our major expenses were our VFD and our spindle. Our VFD is the variable frequency drive. If you don't know what that stands for. After that, we had our mock software, which we were able to get a student discount for, which was very, very nice of them, because that saved us a very large chunk of money. The 80/20, which we had already, if we didn't have it, that would have been a large expense. We came in under the budget that we set for ourselves, $1,500. We're still over the school's budget, to be honest.
All right, so above in the video is playing to the left, you can see a model that was created using Fusion 360. And in that same software, you're then able to generate a toolpath, which is what it's following now. We created the Wilks line W for this. Then we inputted our specific, our tool size, our diameter, what type of tool we're using, things like that. And we were able to generate a G code. The G code is then being executed in the Mach 3 program. It's kind of hard to see from up there, but in the green box to the left is actually the G code being executed. In the center box is the position of our spindle. And in that right box, there is a W. It's kind of hard to see, but that's actually the top view of our part. And it is, you can't see it actually following that position and where the spindle is relative to your part. Now, in this next video is the Wilks line W with that G code actually being ran on a piece of aluminum, which is being passed around right now if you haven't seen it yet. You will, for the purpose of this video, we did speed it up. We were cutting at 0.75 inches per minute. We sped this video up 15 times the length. I think it took about 23 minutes for the part to actually get built out. Now you will see towards the end of this video that it does have a lot of chatter in it. It creates some defects at the end. This error is caused, one, there's a lot of slopping and also binding, but also if the workpiece that you're cutting isn't leveled perfectly, the depth of cut is going to vary from side to side, depending on one side's higher than the other. And then we are going to demonstrate our machine next. Mike's going to turn it on in a second. It is going to be kind of loud. We're actually going to run the same G code that's running up there. We're not going to run it for too long because, like I said, it is kind of loud. But also for this demonstration, we did increase the feed rate so you can see it moving much quicker than it actually did in that video. I'll just wait till you can see it get messed up a little bit. Right there, it skips it.
sure that the torque we were using for each of our lead screw systems from our stepper motors would be sufficient. So using the equation above and at various lead screw efficiencies, we found that at a 50% efficiency, we need roughly 200 ounce inches, where at 80% efficiency, we'd only need around 130 ounce inches. Because of the assumptions we made with this equation, we wanted to make sure that the stepper motors we had would work perfectly. So we got stepper motors that are rated about 425 ounce inches to make sure that there'd be no issue at all with movement. In terms of testing our machine, we want this to be able to use it in educational environments such as the ME 215 class here, the Intro to the Manufacturing Process class. And one of the things that we go over in milling is the amount of material that's removed. So we looked at two different aspects in testing on a 1 inch by 2.5 inches by 50 hundredths inches of a cut. And it's going to cut out the entire box in order to test the amount of volume that our machine should remove versus how much it actually removes, and testing just in one cut how much material is removed and the rate at which it's removed to ensure that even if our machine has issues with binding that affect the overall volume, the material removed is still fine in one pass. So up above, we use that volume equation with the cutting depth, the cutting width, and the cutting length. Note that for the theory and the actual, they're not going to be the same values because of set binding and tolerance. So in the case of the theory, the length would be 2.5 and the width would be 1 inch. Whereas with our actual, we're about a 1/16 off, like we said we wanted to be with our tolerance. So the value is a little bit less. This results in a theory volume calculation of 0.135 cubic inches, whereas with our actual, it's 0.123 cubic inches, resulting in a percentage error of 9. For our MRR, because we were focusing on our material removal rate, which is how much is removed per pass, we didn't want to focus on the overall cutting rate because you take the volume up there and if you divide that by your cutting time, you're going to get around the same percentage error. We wanted to make sure that in the one pass has a low enough percentage error so that it can make one good cut, but as it goes through the entire process, the binding is what's going to cause the larger error overall. From this, we got that our theory would be 6 times 10 to the negative 4th cubic inches per second, whereas with our actual is 6.54 times 10 to the negative 4th cubic inches per second, resulting in a small percentage error. But as I said, when you actually make it go through the entire thing, all that binding is going to add up, and you're going to get a much larger percentage error with your volume in the end.
All right, so just going into some of the results from our testing. In the top left, you'll see this was actually the first piece that we have done with the mill. This was a couple weeks ago. Just a very simple geometric shape. We did start with wood simply because we had a lot laying around. It was easy to use, and it's much more forgiving. As most of us have minimal or no experience with machining like this, we figured if we use wood, it's going to be a much softer material. If we do accidentally cut too deep, or maybe our feeds are a little too quick, it won't be as catastrophic as aluminum. As you can see below, we also tried the Flying W. Again, our speeds and feeds were still not very accurate with the wood Flying W. We even highlighted where some of the errors were, where it crossed over, and it done a little bit too hard. Interestingly, on the top right, as I said, we were trying to get our speeds and feeds right before we got to aluminum, and based on the circle blue error section, we did actually break that tool, which we do have as well if anybody would like to see that. We broke one of the flutes off and we snapped it in half. Since then, we have gotten better. These two pictures are actually the samples being passed around right now if you haven't seen them yet. In the top left, what actually happened there was the Flying W was coming out very well, but we learned during this process that one of our issues with the vise was that we were not properly ensuring that the piece was level within the vise, and when you're dealing with such a small depth of cut per less than a millimeter per pass, basically over 6 or 10 inches, if you're off by even a very small angle, you're either going to start digging in much too deep, or what happened in this case, it won't cut at all, which is why that section is missing. Then in the bottom right, this is the final piece that we are sending around that was in the video as well. And you can see there are a few errors, but again, we got it properly leveled and it did successfully mill out the Flying W.
So, future considerations for this project, one of our biggest ones is cost reduction. We We wanted to try to make building this machine as affordable as possible, but we ran into some unforeseeable issues. We are aware of those issues now, so for future models, it wouldn't be nearly as much as, it wouldn't cost as much as the result of the 1300. Another issue is heat distribution. We have a low feed rate, resulting in one, a long milling time, but also with the low feed rate, a lot of heat is building up. The heat building up not only can warp the cutting part and affect the tolerance, but it can also greatly affect the cuttings when destroyed. So one solution to that would be to apply cooling to the part to ensure that the heat remains at a minimum. Another issue would be with the vibration and damping. The chatter, as you can see with the parts that pass around and with the calculations, greatly affected our effectiveness of cutting with the tolerance. We have linear guide rails, but they aren't the proper linear guide rails we would like. We'd like to implement more effective ones to ensure that the binding is at a minimum. Another issue would be with safety. While we have the protective covering, which is over there, in order to get the chips off, you have to either brush them or you have to completely lift off the covering and use compressed air. We'd like there to be a compartment that you can open up and then with the compressed air blow the chips off. And then our final issue is mainly just implementation. With the chattering issues and all the other combined issues we still need to deal with. While you could use this in a classroom to demonstrate the milling process, we don't want it just to be for demonstration. We want it to be that anyone can take this machine and in their garage use it as a milling machine.
So lastly, we would just like to thank everyone that helped us get this far. Of course, we could not mention everybody, but first and foremost, we'd like to thank our Senior Projects Advisor, Dr. Carole Baddour. We'd also like to thank Dr. Youngsu for some of his help throughout the entire process, as well as the Senior Projects Coordinator, Dr. Berger. We'd also like to thank Dr. Carlos Clean, Mr. Robert Taylor, Mr. Mitch Adams, Mrs. Lisa Colby, and Mr. Tom Bieber. Thank you so much. If you have any questions, please let us know.
We are giving it to Dr. Baddour as we got all the stuff sorted out with IT so that she can use this computer with the program. So yeah, at any moment if she would like to, she could bring it into the classroom and show the milling process.
I have to confess, you guys proved me wrong. So that was a big doubt for last semester. So I think you guys did a wonderful job. It's really impressive. I do have a few technical questions. So for the spindle, what kind of motor? That's an AC induction motor, right? For the spindle, that's an AC induction motor. So what's the range of speed for that?
So speed control is one thing we have been struggling with. We wanted to be able to, so normal milling process is probably right around 2,500 to 3,000 RPM. We've been struggling with controlling spindle speed. We did able to get it down to 7,200 RPM, and it does go up to 24,000 RPM.
Okay, so you are able to control the speed.
Correct. Up to an extent, yes.
Yeah, just not as well as we were hoping.
What kind of driver do you use to control those steppers?
Just a stepper driver that we found online.
I see. You guys didn't mention that. That's why I was.
Yeah, I don't know details about it right now.
Okay. Well, what kind of software are you using for the control interface? The G-code, is that software interface? Is that interface something you can get? Because I know there are many hobbies that share this. Is that something you guys get?
Yeah, so we use Fusion 360, which has a student version. We use that to generate our model and create a G-code. But we use this program called Mach 3, which is a common hobbyist software to run CNC machines, and that's what executes our G-code. Any other questions?
You guys mentioned 3D printing, and you guys compare the price, $5,000. So how do you compare your machine with the similar 3D printers?
Well, the analogy was just how 3D printing has gotten to such a level where it's attainable, I'll say, by the common man. Obviously, $500 is still very expensive, but when you look at small-scale subtractive manufacturing machines of a similar caliber and capability, They're 4 times more expensive, if not more, for the same capabilities that we were able to achieve. So we're trying to work towards bringing that number down.
And my second question, so when you search for 3D printers, did you cross the type of printer that named as laminate 3D printer, sheet lamination 3D printer?
Never even heard of that shit.
That is very, very similar to what you have now. They have the aluminum sheet or reels ultrasonically bound together layer by layer, and each layer you need to subtract anything. You have the similar setup, come and subtractively remove the part, and then next layer do it up on top of that, so that you can create a much taller instead of just a mark. So I'm just
What
just
material
so
would
you know.
that be? What material would that be?
It can be aluminum, can
Okay.
be paper, can be just aluminum paper. And for paper, it can have multiple colors. So,
No, we'll look into it. Yeah, that's all.
so that's a really great reference to what you have.
Anything else?
Great, just to mention, you have 3D work with them. Did you ever test in the Z direction?
Yeah. I can actually jog you in Z direction right now if you'd like to see.
That's okay. No, I'm just. It's not like I want to. No, but the value is just 2D, right?
Well, it has to bring the tool down, otherwise you drag through the entire
Now,
part.
when you're talking, you do not necessarily change the depth.
In between, if you want to go deeper, you do a less per pass, and then go deeper, do the same thing.
Okay, so what if you want to cut something that actually has a 3D feature, like a contour? Is that possible?
Yeah. Like we were cutting wood at much deeper cuts. We could even go deeper than this. We just stopped there. But aluminum, we're struggling with a little bit more. We'd like to be able to do that in the future.
So the motion is there, but then how capable is actually
Exactly.
the motor?
Until you add that 4th axis and actually start turning your bar around or a 5-axis mill, those contours you're not going to be able to get to the same quality with the 3
Because I just saw that you have the Z direction capabilities on. It shouldn't be too hard to actually cut some 3D features stuff.
Yeah, actually,
To a certain extent.
that's sort of a limitation. So you need to have the bigger cross section or bigger cut on top of the smaller cut. You can now do the reverse. But there's a like really high tech. Like it has a movable back that you can rotate it and have the drill to remove this material from some.
To do something like this with a plus
Right,
or minus,
no,
plus or minus 16,
That's like
cut
only
off
one or two
your
companies can do that.
out of the scope of this project.
Thank you very much.
Okay, so we have one more group to present, and then I'd like to offer some closing remarks for the day. The group we have coming, they're actually independent study class working within the semester. They're working for